Seatbelts, everyone! Come on! Ride on the magic scuba!
Hi everybody, my name is Dan Markland. I'm part of Group 19 for Civil Engineering and Hydraulics. My group is with Kevin Diamond and Matt Kowalski, and we'll be doing the homework solutions for problems 2 and 3 of homework number 3. Let's start off right away. First problem is 2.72 from the book. As you can read here, the problem reads, a rectangular gate that is 2 meters wide is located in the vertical wall of a tank containing water as shown. It is desired to have the gate open automatically when the depth of water above the top of the gate reaches 10 meters. So at the distance, what distance, D, should the frictionless horizontal shaft be located on which the gate turns? And what is the magnitude of the force on the gate when it opens? So we're finding the two variables here. So our problem, we're going to find D, the distance of the shaft, F of R, the resultant force there. We've been given the rectangle and the specific weight of water. So let's jump into the solution. What solution we're going to be using is we're going to be using the center of pressure formula. Because we want to find the center of pressure, because at that point is where we want to put the pin, so that the gate will be able to turn, as you can see here, in a counterclockwise direction and open when there's 10 meters of water above. So here is our center of pressure formula. We're going to go ahead and find the variables. I'll tell you about them as we go. Let's go ahead and start with YC. So YC, if we look over here, is the distance from the top of the water to the center of mass, the centroid of the gate. So the distance from the top of the water to top of the gate, 10 meters. And then the center of the rectangle, as common knowledge, as most of we know, is the height of the rectangle, 4 meters, divided by 2. So our YC is 12 meters. Alright, next, we're going to go back and we're going to look at, let's look at A, area. Simple enough. The area is equal to what they gave us, 4 meters times 2 meters equals 8 meters squared. Common algebra. Alright, and finally, we want to find IXC, the moment of inertia around the x-axis. IXC is just a given equation, and as we can see here, for a rectangular gate, it's going to be B times H cubed over 12. And B being the base of the rectangle, H being the height. So, from our rectangle, B is equal to 2, H is equal to 4. So we're going to just plug on in. So IXC equals B, 2 meters, times H, 4 meters, cubed, divided by 12. The answer to that is 10.67 meters to the 4th. So now we'll look and we see we have our moment of inertia, we have our area, and we have our distance to the centroid of the gate. So now all we got to do is just plug and chug. So we have YR is equal to 10.66 meters to the 4th, divided by 12 meters, times 8 meters squared plus 12 meters, and that all equals 12.11 meters. That's what IR is. So now we're wondering, what are we going to do with YR to find D? Well, as you can see from the picture, YR equals D plus 10 meters, and YR, as we just found, is equal to 12.11 meters. Simple algebra, subtracting 10, D is equal to 2.11 meters. So there's our answer to part A. Now, let's look at part B. How are we going to find the force at that location? Well, part B is actually just a simple equation. F of R at a certain depth that we know, which is where we found the center of pressure, is equal to the specific weight of the fluid, water, times H of C, the height to that point, times the area of the object being acted upon. Well, we know the specific weight from our givens, is 9,810 newtons per meter cubed. Multiply it by HC, which is just equal, HC here is the same as our YC value, the distance to the centroid from the top of the water, just different variables, 12 meters. And then the area, as we know, again, 8 meters squared. Multiply it out, plug and chug, and the answer that we get is 941,760 newtons. And there is our answer to part B in part 1, or the first problem.